Dear students, we were discussing about the Gauss elimination method, and we need to write the Fortran code out of it. And to write the Fortran code based on basic Gauss elimination method, it is pertinent to have a short discussion about what we have learned until now. We have seen that a sets of linear equation can be expressed in terms of matrix Ax equal to B, and we have while solving a problem, the problem that has this problem, what we have done is we take a matrix A, all the elements of matrix A, and augment with the matrix B, and here the matrix B is written in terms of A1 n plus 1 because it is 1 n, then it should be, it's n by n matrix, so the last elements of the first row will be 1 n plus 1, and these all elements comprises the matrices of element B. Now our intention, what is our intention? Our intention is to make a upper triangular matrix, and then by backward substitution we can find out all the unknowns starting from x1 to xn, and what are the operation that we have to do so. And to do so, the first operation that we need to do is we normalize the row 1 with the first coefficient of a11, and then we multiplied by a21, and we subtract the row 2 by this row 2 minus the factors. So my a21 prime is equal to a21, that is a new derived system. A21 is a21 minus this factor. A21 by a11 is a factor that has to be multiplied by a11, then a21 by a11 is a factor, so a22 prime should be a22 minus a21 by a11 a12. So the general expression for this we can write aij is equal to the new aij is equal to old aij minus aik by akj. Here the k is equal to 1. So if I say that is a prime 21 is equal to a21 minus a, the factor, remember that is a21 by a11. Here I is 2, k is 1, 2 1 by 1 1, a, k is 1, and j is also 1. So in this way we change the row 2 elements, and subsequently we change the row 3 and up to row n. So after the first operation, our derived system will be comprising of the all the elements. Row 1 will remain intact, but the row 2, the first element becomes 0, and subsequently up to Rn the first row element should be equal to 0. Now the second operation, in the second operation what we have done, we have taken again, we will normalize the a22. So we have normalized the row 2 with the a22, and then my row 3 will be replaced by the row 3 element minus these factors a32 prime by a22 prime, sorry, it should be a22 prime multiplied by r2 by r2 multiplied by a32 prime by a22 prime, and again r4 should be replaced by r2 by a42 prime by a22 prime. Similarly rn should be replaced by rn2 prime by a22 prime. So again the generalized expression, we can see that aij, the second derivative, should be equal to the second derived system, or coefficient should be equal to aij of the first derived system minus aik of the first derived divided by akk of first derived into akj of the first derived system. So after the n operation, what we will see, it turns up into a upper triangular matrix. So this is the upper triangular matrix, and this process is known as triangulation, and by backward substitution we can find out the values of the unknowns. So so backward substitution will start from xn. So the xn value is nothing but an minus 1 by an plus 1 divided by an minus 1 by ann. So if I take because it is the example that we have done is equal, where n is equal to 3, so I can write x3 is equal to nothing but a34 second derived by a33 of second derived system. Similarly, I can find out xn minus 1 and it takes the form like this, and the x2 value we have calculated, it is nothing but 1 by a22 of first derived, a24 of the first derived minus a23 of the first derived multiplied by x3. Similarly, we have find out the x1 expression, and it is 1 by a11 a14 minus a12 x2 minus a13 x3. So all this thing has been discussed earlier. Now we will jump into the Fortran code, but before going to the Fortran code, we must see that what are our general expression, and because we need to write the general expression in our Fortran code. So this has been discussed earlier. So we will initiate a k loop, and k will start from 1 to n minus 1, and my I should start with one increment more than that of k, that is because if k start from 1, my I should start from 2, and I will take j from 1 to n plus 1. So the general expression has been discussed earlier, and the general expression for ak is this, and that has been discussed earlier also. So let us jump into our Fortran code. So for that I am going to the Fortran and terminal. I will write gedit and gauss elimination dot f, and question we need to open an editor, and in that editor, let's see, we will write tab find solution using gauss elimination method. Now we have got the two matrices. First is the A matrix, another is the X matrix, the unknown matrix, because we have augmented the B matrix with the A matrix. So since we will be dealing with an array, so we need to first declare the dimension of the system. So dimension, I write A, then 10, and remember I write 11 in the sense because we will be adding one more vector of the B. So at most, then if A matrix will be n by 10 by 10, then B will be naturally one increment of that. So my augment matrix will be 10 by 11. So A 10 11, and I write X, the unknown matrix of 10. So after declaring the dimension, we will say that okay, then write I will say that enter the dimension of the SYSTM system. So read n. So that we have done the problem which is having a dimension of 3. So I will write 3. That is a 3 by 3 matrix, and we have got 3 unknowns. So basically n represent how many unknowns are there. Then I will say that okay, write the elements of A in row wise. Remember that A is my augmented matrix. It consists of the B matrix also, the element of B matrix also. So I will write enter the elements of A, and I will say that okay, row wise, enter in row wise. Okay, since I will be reading in a row wise, then after initiate do I equal to 1 comma n, that is number of rows should be n, but my number of columns is n plus 1. So read in default format A I comma j, but here the j should start from 1 to n plus 1. Okay, then I stop this loop and do. After that I need to start one loop, do k equal to 1 comma n minus 1. So I can only find the root up to n minus 1, because the last root is defined by we will not take into consideration, we will find out directly. So the operation has to be performed up to n minus 1. Then I have in that case I have to initiate a pivot variable, which is nothing but equal to a k comma k. So for the first if you see our expression, so for the first case my pivot is a11, first operation, then in the second operation it is a22. So that's why my pivot is, whenever it start the loop, that will be my pivot akk. Now I will initiate a I loop, and that okay, it is better to write give a statement number, do 10. Okay, after that you write do 20, and then my I, which is equal to k this k plus 1. I will start from k plus, if k is 1, then I should start from 2, and it will end up to n, isn't it? And after that my factor in this I loop is a I k divided by my pivot, pivot pivot. Now why I am writing this, so why I am writing this, because this is my pivot element, a21 by a11 for the first I, then it will subsequently change to the second I as a31 by a11, and subsequently it will change as an1 by a11 after every I operations. So that has to be included, aik by pivot. Then I will initiate a do 30 j loop. J is starting from 1 to n plus 1. And my ajth element, ai comma j element, ai j element is equal to the new ajth element, is the old aij minus that factor factor multiplied by a then k comma j. So that is the general expression that we have expressed. So we have written this is aij. If you see aij old new aij is the old aij minus the factor. A factor is nothing but aik by akk multiplied by akj. So that is the expression that we have written. After that what we will do, we will say that okay, my j loop continue, then my I loop should continue, and then after my 10 the k loop should continue. So okay, now we can check whether our matrix has been triangularized or not. I just write a comment statement and I'll say that okay, check for triangulation. Triangulation. So if we need to check whether my triangle, whether my matrix obtained is upper matrix or not. So I write I initiate one do loop, do I equal to 1 comma n, then write then I comma j comma j is starting from 1 to n plus 1, and and do, and I stop here to see stop and end. Let's save it, and again we go back and compile it. G-F-O-R-T-R-A and G-Fortran dash O gauss elimination dot F. Okay, it has been completed, no error. Gauss elimination. So in the dimensional system we have used 3-dimensional system, and now I have to enter the row wise the elements. So what were our elements are? Come to the problem. So we have got 3 to 110. So right here, so 3 space 2 space 1 space 10, then 2 space 3 space 2 space 14, and then 1 space 2 space 3 space 14, then enter. So we see that my triangle is my matrix after the operations, it has become a upper triangular matrix. So the code that we have written is working properly. Now again we go back, and because we need to find out the unknowns, so what we will do here, we will write C, and we will write that back substitution, substitutio, back substitution. Okay, in back substitution, what we will be doing, the first root x n is equal to my again we come here, it is my last root is a n plus 1 by a n of the n minus 1 derived system. So I will say here xn is equal to a n comma n plus 1 divided by a n comma n. So that will give you the value of the nth root. Now to get all other nth unknowns, now to get all the other values, other unknowns, we have to initiate again a do loop. Do, I write 30, then 40, k will start from n minus 1 to 1, it will go up to 1, and with a decrement of 1, so minus 1. After that what we have to do, we have to make again we see here, we have to initiate a sum counter, because we will be repeatedly summing. So sum counter is important, so I write sum equal to 0. After that I write do 50, 40, 50, okay, 50, and j will go from k plus 1 to n, because now previously I, but now j will go from k plus 1 to n, and we have got sum, the new sum is the old sum, in the counter it will add up, plus akj multiplied by xj. So again I will see here why we are writing. If we go to the generalized expression, again we are seeing that here it is akj into xj, and j will start from k plus 1 to n. Okay, so my j is starting k plus 1 to n, and it is akj times xj, and once the j operation is completed, we will write 50 and continue, and after that x k, my new xk, come to the expression, my new xk, all the others values of the x is equal to akn plus 1 minus the sum that we have obtained and divided by akk. So I will write here the expression axk is equal to bracket a k plus 1, sorry, k and k to n plus 1 minus the sum that has been obtained divided by a k comma k, akk. Then I will write 40 because all will be continue. Continue. So now we come to the result section. So what result we will obtain? Results. All the values of x are stored in xk, so we need to just read it out. So write the solution vector is do I equal to 1 comma n, write my, I will write here I and xi, but with the format. So I write we have done up to 50, so write 60. I will write in terms of a format 60 tab format format format. In that format I will write x I will write I2 bracket and that is f, I'll write f 5.2, that will do, and format f 5.2, and then it is stop and end. So control S, we save it, again we compile it. Sorry, there is no undo statement, so do write. Okay, we can write here also and do control S. So it runs gauss elimination. System is 3, again 3-2-1-10 and 2-3-2-14, then 1-2-3-14. This is our result. So my solution vector comes out to be 1, 2 and 3, and that is in agreement with the previous result that we have obtained. But while doing so, we need to know that there is a sometimes it might happen that my pivot element became akk became 0, so for that rearrangement is required. Thank you for watching.